In the last video, I've talked about how when this coil rotates by 180 degrees, we must take it that the flux, the magnetic flux going through the coil, has changed sign. Now this description, the way I did it, and I described it, is nothing more than a way to do the calculation. But what is actually the physics involved? How does this happen as a result of Faraday's law? Because whatever happens around here when the magnetic flux through the coil changes, whatever happens here must completely depend on Faraday's law of electromagnetic induction. So how does that lead to this way of calculation? So what we need to do, therefore, is to understand the situation physically. So what I'm going to do now is to look at this situation more closely. Look at what happens when I rotate this by 180 degrees. Let me clear this up. Right, so what I'm going to do is this. I'm going to draw a few pictures. Okay, starting from this one, where I have a loop. I have this square loop down here. Okay, now, so this square loop is in this vertical position. Now let me put in some labels so that we can keep track of the motion. Let me call this corner letter A and letter B, and call that corner letter C and letter D. Now I would need to think of this as connected because I want to talk about a current flowing around the loop. So let's imagine that it's still connected to a voltmeter. And again, we are using flexible wires so that these wires can twist and turn as this rotates. Okay. And what I'm going to do now is I'm going to start rotating this. So let me try and imagine what happens if I rotate it. Now I'm going to draw a few situations. I'm going to draw what happens when it has rotated by 90 degrees, starting from 0 degrees. I'll call that 0 degrees. And then rotates by 90 degrees, and then it rotates by another 90 degrees to a total of 180 degrees. Now I'm going to draw in the magnetic field. Just going to draw 3 lines to represent the magnetic field. So magnetic field has not changed. The flux density is the same. It's 1 Tesla here, 1 Tesla here, 1 Tesla here, uniform field. Okay. But the coil has rotated by 90 degrees. So it is now horizontal. Okay. Horizontal. Right. And now we need to keep track of the sides, and so I'm going to follow the corners as it rotates. So that DC would have come down here, DC, and AB would have rotated to here, AB. Okay, so connection here, let's see, might have just that. Okay, and then when it rotates until it's 180 degrees, let's see, it's rotating this way. It's rotating this way. So it's going to become vertical again. Vertical. Again. Okay, and this time, as it rotates, AB now moves to the top. Use green letters. AB moves to the top and CD moves to the bottom. Okay, I still have my connection to the voltmeter. Okay, so I just assume that the wires would sort of twist around as this rotates. Okay, now what I'm going to do is this. I'm going to think about how the current flows as I rotate from here to here. How does the current flow? We know that there's a change in flux from here to here. The size of the flux here is B times A, where the B is the 1 Tesla, and the A is the area of the coil. Okay. Now, when I'm here, the area is again perpendicular to the field, even though it has rotated by 180 degrees. So the flux here is again BA. That's the magnitude of the flux. So I'm not going to worry about any plus or minus signs for now. When it is horizontal, as we understand, the flux just passes along the surface. No flux actually goes through the surface. So therefore the flux is 0. So so these values here are the flux linking the loop. Okay. We know how to calculate the induced voltage at each of these stages. So, for example, I'm going to just follow my previous example in which I took the time that it rotated from by 90 degrees to be t equals to 0.005 from here to here, and another 90 degrees, another 0.005 seconds. Okay, so what I want to do now is to figure out what the direction of the current is in this loop. Does it flow this way or does it flow that way as this rotates to here? Right. As it rotates to here, think about how this changes. You have this magnetic field going to the right, and you have the area perpendicular to it. As this rotates by 90 degrees, the magnetic flux decreases to 0. So there is a decrease in the magnetic flux going through here. Okay, so according to Lenz's law, the direction must be in such a way as to oppose this change. Now, this change in this case is a decrease in the field, in the flux. So to oppose this change, the current must try and increase the flux. In other words, the current must flow in the correct direction so as to produce a magnetic field in the same direction as the original field. Right? As it wants to try to oppose the decrease. And to oppose the decrease, it will oppose the decrease by trying to increase it back, in a sense. So what direction should the current be? Okay, the current should produce a magnetic field in this direction, and to determine that current direction, we can use the right hand thumb rule for this coil. So we should stretch our right hand, put our palm next to this loop, point our thumb in the direction of the magnetic field, and wrap up the fingers of our right hand around the loop. If you do that, I believe you'll find that your fingers would be pointing in this direction. Okay, so therefore this is the direction that the current would start to flow in as it rotates from this position to this position. Okay, now let's move from this position to this position. As I go from here to here, the magnetic flux would increase from 0 to the value here. So it would increase along this direction. Right? It would increase along this direction as it rotates from here to here, as the coil flips up vertical again. So this magnetic flux from the north and south pole, from the two magnets next to the coil, would lead to an increase in the magnetic flux as this coil rotates from here to here. Since the magnetic flux increases, the induced current would try to oppose that. So it would try to reduce the flux going through the coil. Now, to reduce the flux going through the coil, it must therefore produce a magnetic field in the opposite direction. So once again, we take our right hand, stretch our right hand, place the palm of our right hand next to the coil, point the thumb in the opposite direction to this field, and wrap the fingers of our right hand around the loop. So and if you do that, you'll find that the current should flow in this direction. So on its way up from here to here, the current would start flowing from A to B in this direction. Okay. So this direction represents the flow in between here and here, just as this direction represents the flow in between here and here. Okay. Actually, at this instant, the current may not start flowing yet. It's only when you start rotating that the current will start flowing. So what we have here is therefore a current that flows this way. Now, if you look at these two loops, it's a little bit tricky, but you can tell whether the current, or the current looks as if they're flowing in opposite direction if you compare this top edge of the loop with this top edge of the loop. See, the current on the top edge is going this way, alright, going this way, whereas the current here is going the other way. But we should not compare the top edge of the loop. We should compare the corresponding, the same edge of the loop, meaning that if you're looking at CD here, we should look at CD here. Alright, we should look at the same edge. Now, if you look at the same edge, the current is flowing from corner C to corner D during the first 90 degrees. And in the next 90 degrees, the current is flowing from C to D again. So in other words, as far as the loop is concerned, the current has not changed direction. The current continues to flow in the same direction. Okay. So this means that if I want to determine the voltage between here and here and the voltage between here and here, the voltage also has not changed direction from here to here and from here to here. Now, how would I calculate the voltage? Right, let's try it. Suppose I want to calculate the voltage between here and here. What I would do is I would take V. Between here and here, I would do, what would I do? I would take the final voltage. Okay, let's say I would minus the final voltage minus the initial, final flux minus the initial flux between 0 and 90 degrees, which is BA. And then I would divide by the time taken. That's how I would do it. Okay. Now, if I do this, the answer I get from these numbers, right, which I've calculated in the last video, would be, in this case, minus 2 volts. You can put in the numbers. B is 1. A was taken to be, let's see, this side is taken to be 10 centimeter. Okay, and that's a square, and T is this number. So if we put in the numbers, we'll find a minus 2 volt, the minus sign coming from that. Now, if I calculate the voltage here, what would I find? I would have to take BA, and final flux minus the initial flux, right, between this point and this point. So I get minus 0 divided by T. Now it's the same numbers that we use. The only difference is that I have a minus sign here and I don't down here. So I would get just 2 volts. Just 2 volts. Okay. But because we understand that the current really flow in the same direction from here to here and from here to here, what this situation suggests is that we should really try to make our formula work in such a way as to give the same signs of the voltage. Because if we start getting opposite signs, it might mislead us into thinking that the voltage has changed direction. Okay, and in order to to get the same sign, in order to get the same sign, the way it is done is to say that I should change the sign of this flux. So in other words, we are actually making up a rule here. We are making up a rule. Right? We need a rule to help us to calculate this formula. Now, this rule is a bit like, when I talked about acceleration and velocities many videos ago. I talked about how when you're moving along a straight line, you should choose either the right side or the left side to be negative. So that was a rule, right, that helped us to use the acceleration equations. Now, in this case, this is a rule. I would have to choose a minus sign here. But how do I know that I have to choose a minus sign? Well, the way is this. The way to do it is this. Was to use the way that I described in the last video, is to imagine that the area of this loop, this coil, is to think of one side of the coil. And in the previous video, I chose this side. Okay, let's think of an arrow that's perpendicular to the coil. Now, as this rotates, the arrow rotates with the coil. So when it is here, when it's horizontal, the arrow points downwards. When it has rotated by 180 degrees, this arrow now points the other way. Okay, and when we think about this physical situation, we see that in the beginning the arrow points in the same direction as the magnetic field, and in the end the arrow points in the opposite direction. So basically we are in a way just following the side of one side of the area. Alright, in the beginning the area, this side is towards the right, but after it flipped over 180 degrees, that side is now facing the left. Okay, so what I'm doing is I'm just using this rule. If you like, in a way, I'm just using this arrow as a way to keep track of whether this face of the loop is on the right side or on the left side. Okay, so by following one side of the loop, okay, and checking whether it's on the right side or on the left side, we can then use this idea to give a sign. So I can say that when one side of the face is in the same direction as the magnetic field, I give the flux a positive sign. When that side is on facing the opposite direction to the magnetic field, I would give the flux a minus sign. And you might ask, so how do I know which side to choose for the how do I know which side to choose as the positive side? Well, doesn't matter. In the same sense that when we did our acceleration calculations for motion along a straight line, it did not matter whether you choose the right side or the left side as negative, as long as you choose one side and you stick to it in that problem. So it's the same here. If instead of choosing this side, I have chosen the opposite side, it just means that when I work through this calculation, all the signs will be reversed. Okay, so if I've chosen this side as it is, then I need to put a plus sign here and a minus sign here, and when I work through this, I get a minus sign here. And the two minus sign here tells me that the two voltages are in the same direction, and that suggests that the currents are in the same direction in the coil, which is correct. What if I've chosen the opposite side as the positive direction instead? What if I've chosen to follow the opposite side? If I've chosen to follow the opposite side, then the signs will change. So that will change to minus, that will change to plus. Okay, and minus will give me plus here, and plus here would be a plus here. So I'll end up with plus 2 volts and plus 2 volts, and they're still in the same direction. So physically, the important thing is that these calculations this rule, this approach allows me to tell whether the voltages and currents are in the same direction.